Hey everybody, this is Dr. O and welcome to this solution set for homework from Chapter 3. Let's get started. All right, so here we are for our first practice problem, our for practice problem, and which is your homework problem. And they want us to write the electron configuration for each of the elements below, and we're going to start off by looking at chlorine. Now, if we look at chlorine and we were to look at it in a periodic table, and you do have one of these in your textbook on the cover, on the inside of the cover, we can see that chlorine is in the third row, and the rows tell us about the number of orbitals we have to populate. So we're going to have 3 orbitals for chlorine. All right, so how many electrons can each orbital hold? Well, the first orbital can hold up to 2 electrons, the second orbital can hold up to 8 electrons, and the third orbital can hold up to 18. Although we fill the first 8 first, and then go do something else, and then come back and fill in the last 10. And we're going to look at an example with that. Now, how many suborbitals how many electrons can each suborbital hold? Because I have them listed out for you within each of the orbitals. Well, every s subshell can hold 2 electrons. Every p can hold 6 electrons. And every d can hold 10 electrons. All right? So that's our foundational information right there. Now, if we go back to the periodic table, we take a look at chlorine. We know that chlorine has an atomic number of 17, which tells us that we have 17 electrons that we need to find homes for. All right. So I'm going to bring up a picture of chlorine with its orbitals, and I'm going to bring in 17 electrons, and we're actually going to populate the orbitals as we fill in the numbers for our electron configuration. All right, so we always start by filling in the first orbital first. So we're going to bring up 1s. So the first orbital only has an s subshell, and we know that that s subshell can only hold 2 electrons. The first orbital can only hold 2 electrons, and so we're going to let our reader know that by writing a 2 in the superscript of our 1s. We're done with the first orbital. We now need to move on to the second, and the first subshell we're going to fill in is the s in our second orbital. And we know that every s can only hold 2 electrons, so we're going to grab a couple of electrons and drop them into that second orbital. We're going to let our reader know that by writing a 2 in the superscript of our 2s. Now we have to populate the 2p. So every p can hold up to 6, and we have plenty of electrons to work with here. So we're going to drop 6 electrons into that second orbital. We're going to let our reader know that we've done that by writing a 6 in the superscript of that 2p, and we're done with our second orbital. We've got 8 electrons in there. We've got 2 in the s subshell, we've got 6 in the p, and that gives us a total of 8. So now we have to move on to our third orbital. We're going to start by populating the 3s subshell, which means we're going to grab a couple of electrons, and we're going to write a 2 in the superscript of 3s to let our reader know that that's what we've done. So now we need to move on to 3p. 3p can hold up to 6 electrons, but do we have 6 electrons here? I believe we only have 5. If we count them, we've got 1, 2, 3, 4, 5. Let's go ahead and drop those 5 in. And we're going to let our reader know that by writing a 5 in the superscript of our 3p. And we have now completed our electron configuration. Now, that's a lot of work to go through every time you have to do one of these, particularly when you get to something that's in the third or the fourth or the fifth row. So is there a simpler way to do that? There sure is. So let's bring up our periodic table here. And here's chlorine down in the lower right-hand corner. And we said that if we counted the number of rows, that would tell us the number of orbitals, and we can see that chlorine is in the third row. Now, what else can we deduce from this periodic table, because there's more information here to reveal? Well, if we look at the columns, that tells us something. So for example, these first 2 columns right here, that corresponds with the s subshell. If we come over here to the last 6 columns, that corresponds to the p subshell. And this dippy-any region right in the middle, that corresponds to the d subshell. So if we were to look at the chart now, knowing what we know that for chlorine, all of these rows, the first 2 rows, are going to be filled. The third the third row subshell S is going to be filled, and then we're going to have to count out how many electrons to put in the P. So we could have just as easily said, okay, first row is full, that's going to be my 1s2. My second row is full to the s and the p, so I'd write 2s2 and 2p6. I'm full at the s in the third orbital, so 3s2, and I have to count out my electrons for the p subshell, and I've got 1, 2, 3, 4, and 5. So much simpler, isn't it? Now, if you look in the textbook, they're going to give you an alternative way to write this. And it has to do with looking at the point at which all of the rows are full. And if we look at the rows that are full for chlorine, the first row and the second row are full. And the element that has all of its orbitals full through the second row is neon. Now, everything that we see in this last column is special because they all have full valence orbitals. They have full valence shells. So helium has a full first orbital. Its 2s is full. Neon is full all the way through the 2p. Argon is full all the way through the 3p. All right. So what we could do is we could take neon and see this part right, I jumped the gun. So this part right here corresponds with neon. In our electron configuration of chlorine, this corresponds to neon. So we could eliminate all of this and just simply write neon, the symbol for neon in the brackets, and then go ahead and fill in the rest of the third orbital, letting our reader know that we have a full 2s for chlorine, and that we had to fill in 1, 2, 3, 4, 5 in the p orbital for chlorine. So this is a shorthand notation for writing out chlorine. Let's take a look at another one. Now the second element they want us to work with is silicon, and if we look, silicon is in the third row, which means we've got 3 orbitals. In fact, it's just a couple down from chlorine, and I've got it highlighted there for you. And if we look at the atomic number, it's 14, which means we've got 14 electrons that we're going to place. Now I'm not going to bring up a diagram and drop in electrons this time. We're just going to work from the table. Now we know that we've got a full first row, a full second row, so we can just write that in. So we're going to write 1s2, 2s2, 2p6. All right, so now we have to move down to 3s. Here's our 3s right here. It's full, so we're going to write 2 there. But how many do we have in our 3p? Well, we've got 1, 2, and we're done. Wasn't that so much easier? And as we saw with chlorine, we could come here to neon, and we know that neon is represented by all of this, so we could just replace all of this with the neon, write the symbol in brackets, and then bring down our 3s2 and our 3p2, and we've got a second way to write silicon. Let's take a look at another one. All right, our third example, our third element they want us to take a look at is strontium. And strontium I have highlighted for you, and we can see that it is in the 1, 2, 3, 4, 5th row, which means, ooh, we got 5 orbitals. That's exciting. 5 orbitals to do. And if we look at it, we can see that it has an atomic number of 38, which means we've got 38 electrons that we have to fill. All right. Now, we know that the first 4 orbitals are full. The first 4 rows are going to be full, but how do we fill those? Because when we get down here into this section right here, we have a different way that we fill these. So we don't just simply fill the 1s and then the 2s, the 2p, the 3s, the 3p, and then go to 4s and then whatever this is and then 4p. There's a way that we do that, and that has to do with this chart right here. All right, so we're going to fill the 1s first, and then we're going to fill 2s, and then we're going to fill 2p and then 3s, and then we're going to fill 3p, but we're not going to fill 3d. We're going to go to 4s, and then we're going to come back to 3d, and then we're going to fill 4p, and then we're going to fill 5s. And we stop with strontium at 5s. All right, so why do we do this? Well, it has to do with the energy levels. And Mother Nature is a drama queen, certainly, but she's also a little bit lazy. and she likes to have low energy systems come into play before high energy systems. It just creates more stability. So 1s is a lower energy state than 2s, and 2s is lower than 2p, and 3s is lower than 2p, and 3p is lower than wait, I'm saying it wrong. So 1s is lower than 2s, 2s is lower than 2p, 2p is less than 3s, 2p is less than 3s, 3s is less than 3p, 3p is less than 4s, and then 3d is actually less than 4p, and 4p is less than 5s. So the lowest energy state is going to be filled first, and they're not sequential based upon the orbitals. You have to have a chart like this to understand how to fill things in. So let's do that. So we know that our first orbital is full, 1s is going to have 2. We know that the second orbital is full with our 2s2 and our 2p2, 2p6, and we know the third orbital is full with our 3s2 and our 3p2. But if we come to our chart, we're not going to jump in to fill 3d. We're going to skip over to 4s, and we're going to drop that in next. So 4s2, and then we're going to come back to our 3d, and we're going to drop in, because it's full, so we're going to drop in 3d10. And now we're going to fill in 4p, because 4p is full. This is our p over here for 4. So we're going to drop in that 4p6, all right? And then we're going to fill in 5s. And if we look at 5s, 5s is full. So drop in 5s, and with that we're done. Give you a second to digest that. So what does this mean? Well, it means that here is the 1s, here is the 2s, here is the 2p, and we know that when we get to 3 we have to account for a d. So here is 3s, here is 3p, and then here is 3d. All right. So we in fact did fill in 4s, come in and fill 3d, then filled in 4p, and then continued on into 5s. Now, could we have written this even more simply? Yeah, we could have come over here to krypton, dropped in that abbreviation, and then just write 5s2. Let's look at another one. Now, after that last one, this one's going to seem super simple. It's oxygen. Oxygen's in the second row, has 2 orbitals. It has an atomic number of 8, which means 8 electrons. And we know then that our first orbital is going to be full, 1s2. We know that our 2s is full, right? And then how many are we going to put in the p? 1, 2, 3, 4. 4 in the p. Now, could we write this another way? Sure, we could. Not really necessary, but we could. We could do the abbreviated thing where we would take helium, drop it in right there, and then bring down the second orbital information. And we've written the shorthand version of oxygen. All right, and with that, we are done with the first question. All right, so here we are, 3.2. They want us to write the orbital diagram for argon and determine the number of unpaired electrons. So I always like to write out what my focus is, argon. And if I look here at the periodic table, I can see argon's right here at the end of the third row. Third row means 3 orbitals. It has an atomic number of 18. I've got 18 electrons that I'm going to have to place in that diagram. And when we're talking about the orbital diagrams, we're bringing up something that looks like this. All right, where we've got a square for each of our pairs of electrons that have to populate the various subshells. All right, so our first 2 electrons are going to go in 1s, and we're going to have one going this way and one going that way, and then we're going to populate 2s with pairs going in opposite direction. Now we're at p. So how do we populate p? Do we fill the first square and then the second one and the third one? No, this is the kids on the bus rule, where everybody's going to try to get a seat of their own by themselves until the bus starts to fill up, and then you have to double up. There you go. So now we filled up our 2p orbital, and we've got 10 of our 8 electrons that we needed to place. So let's place another 2 in the 3s. That's 12. And then we've got 13, 14, 15, and other kids on the bus rule, 16, 17, and 18. So we have placed all 18 electrons in our orbital diagram. Now the question was, do we have any unpaired electrons? And the answer is no. But could we have predicted that without going through all of this? Well, as a matter of fact, we could have. And the reason why is that anything in that far right column, it's called column 8A, has a full valence orbital, which means that there will not be any unpaired electrons. So for problem 3.3, they want us to write the electron configuration for phosphorus and then identify the valence electrons and the core electrons. And I guess first of all, we need to be able to identify what valence and core electrons are. Well, we've talked a lot about valence electrons in this particular chapter, and we know that those are the electrons that are going to be in the outermost orbital. These are the ones that drive chemical reactions, and the core electrons are going to be all the ones that are in the full orbitals that are going to be on the inside. So that's how we can define that. So whatever's in that outermost orbital is going to be what is the valence electron. All right, so always like to write out my information. So we are going to write out the electron configuration for phosphorus. If we come to the periodic table, we find phosphorus right there. It's in the third row, which means we got to deal with 3 orbitals. It has an atomic number of 15, so we have 15 electrons that we need to place. Now we know that the first 2 rows are going to be full, so we can write 1s2, 2s2, because these are all full, 2p6, all right? And then when we get to this third row, we know that the s orbitals are full, so 3s2, and then we have to figure out how many orbitals we have in p. We've got 1, 2, 3. So we're going to write 3p3. Now we know that if we stop here at the end of the second row that we've got neon, and up to neon is our full valence shell, so we could write this abbreviating neon and then bringing in this incomplete third orbital, and that's another way that we could write phosphorus. All right, so the reason why I did that is because having an understanding that up to the point of neon we are full, that's really identifying our core electrons. So everything right here, these are core electrons. And we can count how many core electrons we have because they are noted in the superscript here. So 2 plus 2 plus 6, 2 plus 2 plus 6, that means we have 10 core electrons. And then everything beyond that, right here in the third orbital, those are going to be our valence electrons. And we can count what's in the superscript here. 2 plus 3 is 5, so we have 5 valence electrons. All right, so here we are at problem 3.4, and they want us to use the periodic table to write the electron configuration of bismuth. So bismuth is located way down here in the lower right, and we are in, I believe we're in row 6. Yep, row 6. And let's go ahead and identify the nearest noble gas that precedes it, and that's going to be xenon right there. All right, so if we look at what we've got bismuth is in the 6th row, which means we got 6 orbitals we're going to have to populate. So we know right there it's going to get a little complicated. We've got an atomic number of 83, got 83 electrons that we need to account for. All right, so because we're going to be using the periodic table and not actually counting the electrons, what we're going to be using is this information right here. Knowing that the first 2 columns represent the S subshell of whatever row we're in, whatever orbital we're in, that the last 6 columns to the right represent the P subshells in whatever orbital we're in, that the D shell, the D portion, represents the D orbital, and in our case, what we know is that everything above this point right here is going to be full. So everything in row 5 is going to be full. So our 5s, our 5p, when it comes to the D is not the same number as the row, it's the preceding row. So that would be 4D, all right? So all of that's going to be full. What we're going to be concerned with is the 6s, the 6p, the 5D, and then if you pay attention right here, there's a whole other couple of rows that represent the F subshell, and this is going to be found in the 4th orbital. So we're going to be concerned with the 4F subshell. All right, so that's new. We haven't dealt with that yet. So let's bring back this particular chart, this chart that allows us to figure out the order of electrons filling these subshells, and let's work with that. All right, so we know that we're going to have everything is full up until the 5s, and that we're going to stop right here with the 6th orbital. So we know we're going to populate 6s and 6p, but we don't have anything in 6d. So we're going to stop at 6p because our bismuth is located in the p section of row 6. All right, let's get started. So we know we're going to have 1s2 because that's full. We're going to have 2s2. We're going to have 2p6 because that's full. 3rd row is also full. So we got a 3s2 and a 3p6. Now this is where things get a little bit odd because we don't go straight into the D, even though it's in the same orbital. We're going to now go and fill 4s. So we're going to have 4s2. And then we're going to come back to 3d, and we're going to have 3d10 because it's full. We're going to now fill 4p, which has 6 because it's full. And we're going to fill 5s, which is also full with 2 electrons. All right. Now we're going to come over here and we're going to start to fill in 4d. Got 10 electrons here. We've got 6 electrons in 5p, and we got 2 electrons in 6s. Right? And now we're going to incorporate 4f. How many electrons can an f orbital hold? It can hold 14. And then 5d can hold 10. And then this is where we are. Bismuth is located in 6p. So how many electrons are we going to put in 6p? 1, 2, 3. Now we know that everything up to this point right here, at the end of row 5, so the end of row 5 where we are allows us to stop at the 6p. I mean the 5p, I'm like, that ain't right. That is going to correspond with xenon. So we could substitute all of this and just write xenon and then set about filling out row 6. And row 6 would be 6s2. Here's our f, 4f, 14, our 5d10, and then our 6p, 1, 2, 3. There you go. So that's how you do something complicated like bismuth. Now, I don't usually work the for more practice problems, but I'm going to. That's what we're going to do next. So let's have a look at that one. All right, the 4 more practice problems are not part of the required homework, but sometimes they're fun to do, and I thought this one would be a good example to work through in order to come up with another electron configuration using the periodic table to help us figure it out. And in this case, they want us to come up with iodine. Iodine is found here in the lower right of the periodic table. I have it highlighted in red, and it is found in row number 5. And the halogen that precedes it is going to be krypton. All right, so let's write all that out. 5th row, which means 5 orbitals, atomic number 53, 53 electrons we need to place. And we know that we're going to be looking at the columns to help us out with this, and we're going to be concerned with the S, the P, and the D. We don't have to worry about F in this case because if we look at row 5, there is no mention of F. We don't get into F until we get down here in row 6. So we're just going to be worried about completing the details for 5S, 5P, and 4D. All right, let's bring up our little chart and let's get started. So we're going to have, let's see, we're going to fill in everything all the way through 4P. That's what we're going to fill in. So we're going to start with 1s2 and 2s2 and 2p6 and 3s2 and 3p6. Now we know at this point we're going to not go to 3D, but we're going to go to 4s2 And then we're going to come back to 3D, and that's going to be 10. And then we're going to fill in 4p6, so 4p6, and that takes us to krypton. And then we're going to start here in the 5th row, and we're going to be filling in 5s2 and 4d10. And then here we are in 5p, and we're going to be filling in 1, 2, 3, 4, 5 electrons for 5p. All right. Now we knew a moment ago when we got to 4p, we were basically talking about krypton, which means that if we'd wanted to do that shorthand notation, we could have just simply written out krypton and then gone to row 5 and filled in 5s2, 4d10, and 5p5. So problem 3.5 wants us to predict the charges on these elements based on, if they were to form ions, based upon each main group element. And there's a couple of ways that we can approach this. And what I'm going to do is I'm going to draw out the electron configuration. We're going to kind of examine what's going on here and tie in some information that we've already learned. We're going to start off by looking at nitrogen. All right, now we know that nitrogen's right here in the periodic table. It's in the 2nd row, but we're not going to really worry about the atomic number and all the electrons. We're going to really focus in on what's happening in that 2p subshell. All right, so if we were to draw out the electron configuration for nitrogen, it's pretty simple. We've got 1s2, we've got 2s2, and we've got 2p with 1, 2, 3 electrons in it. So there we go. All right, so if we look at what we've got here, we've got a full first orbital, but we've got an incomplete second one. All right, so we know that this second orbital could hold 8. We've got 5 in there, and if we focus on what's happening in 3p, that's really where the incompleteness is. All right, so the 2p orbital can hold 6 electrons. 2p in this case only has 3 in it, so 2p3 orbital of nitrogen will have a tendency to gain an additional electrons to become 2p6. All right, so if we look at what's happening here, indeed we are looking at what's happening in p, but we really have to consider the entirety of this row. Right, so the entirety of this row is that we could take on 8 electrons, and we're already mostly full by having 5 in here. So we're kind of past the halfway mark of 8, and it would just be simpler for us to gain an additional 3 electrons than it would be for us to completely eliminate these 5 right here. Okay. Another way we could look at this is to do an orbital diagram and see how the electrons feel. So we know that in the first orbital it looks like this, and the second orbital, the s electrons are paired up. But for nitrogen, in the 2p orbital, in that second orbital, in the p subshell, the electrons are going to look like this. Now that's a reasonably stable configuration, but there's that drive to create the octet, which means that nitrogen either wants to share 3 electrons with somebody, or 3 somebodies, or it wants to gain 3 electrons. Because when it gains an additional 3 electrons, now it's got that octet, that full valence shell. And that is actually a much more stable arrangement for nitrogen. So nitrogen as an ion has a tendency to gain 3 electrons. That brings with it a negative charge. Each one brings a negative charge, and since we got 3 of them, we would write nitrogen with a 3 negative in the upper right to indicate that our nitrogen has gained those 3 electrons and is now an ion and has created stability for itself. Let's take a look at another one. All right, so now we're going to be looking at rubidium. And rubidium can be found down in the 5th row in the first column. I've got it highlighted in red. We know that it is going to has an electron occupying the s subshell, and that's it. And that's what we're really concerned with. So if we were going to draw out the electron configuration for this, we're going to go to the preceding noble gas, which in this case is krypton, and that's in row 4, at the end of row 4. And then we're going to start to fill in the 5th row, which in the case of rubidium is going to mean we only have 1 electron in that 5s subshell. All right, that subshell S in the 5th orbital. All right, so we have to ask ourselves, what is the state of this 5th row? Okay, how many electrons do we have here? Now, the possibilities of the electrons that could populate that 5th row include having electrons in the 5s subshell, in the 4d subshell, and then in the 5p subshell. That's a lot of electrons. And out of all of those electrons, we only have 1, right? So even though the 5s subshell can hold 2, the entirety of that row could hold a lot more. I believe it could hold 20. So then we have to ask ourselves, would it be easier for rubidium to gain an additional 19 electrons to complete that 5, get to the point where the 5p orbital is full, or would it be easier for it to just lose the 1? Well, we've actually thought about this before, and any element that has its valence electron in the s subshell, it's going to lose that electron. So S subshells are going to lose electrons, and when they do that, they're going to ultimately resemble the preceding noble gas. And we all know that noble gases have full valence electrons and create a very stable configuration for themselves. So when rubidium eliminates that 1 electron, it's going to form a positively charged ion, and it's actually going to look, its electron configuration is going to look identical to krypton, because it'll have 18 electrons, not 18, 38 electrons at that point. In question 3.6, they want us to determine which is the larger atom in the pair that we're given, and we're going to make that determination looking at the periodic table. So we have to know some trends. So what are the trends? Well, one of the trends is that elements off to the left are larger than the elements off to the right. So within a row, the element that is off to the left is larger than the one off to the right. Now, why is that? Well, it has to do with how many protons are in the nucleus. So the more protons there are in the nucleus, the greater the nuclear effect is going to be, the greater the pull that all those protons are going to exert on the electrons that are in the orbitals. All right, so that's why. So you look at an element off to the left, and you don't have as many protons there, so you're not going to be pulling in the electrons as closely, so they'll have a tendency to be a little bit more spread out, versus an element that's off to the right. More protons, more nuclear effect, going to pull those electrons in a little bit more closely. All right, what about going down a column? Well, there's a trend here too, and the trend is that you get larger in the size or the diameter of your atom as you move down, and the reason why is because you're adding orbitals. All right, so let's take a look at our first pair. Our first pair is tin and iodine, and these are in the same period. They're in the same row. So we know that whoever's to the left is going to be the larger atom, and that is going to be tin. Our next pair is germanium and polonium, and just so you know that these were named after the country of origin that the person who discovered them was from, I believe is how that worked. It's either that or where the country where they were discovered, Germany and Poland. So if we look here, we've got germanium, which is closer to the left, which would make it the larger in that way, but polonium has an additional 2 orbitals. And with this case, you might be inclined to say polonium, but the author says there's really not enough distinction between them to really know. So this is one where we really can't determine, because we've got germanium being a little bit further to the left, and we do have those 2 additional rows, but polonium is further to the right, and so it's like, are they canceling each other out? Can we really make a clear distinction? And the answer to that is no. All right, what about our next 2? We've got chromium, we got tungsten. Well, these are in the same column, so we can make a determination. The one that is the lower one is going to be the larger one, and that's going to be tungsten. And then our next 2, we've got fluorine, we've got selenium. And in this case, you might say, well, this looks a lot like germanium and polonium, but if we look, fluorine is higher up than selenium, which would make it smaller, and it's also further to the right, which would make it smaller. So in this scenario, fluorine is going to be smaller than selenium on 2 accounts. It is further to the right and is higher up. Selenium is larger on 2 accounts. It's further to the right and it's lower down. So selenium is clearly the answer to this one. All right, 3.7, they want us to write the electron configuration and the orbital diagram for each ion and then make a determination if it's going to be paramagnetic or diamagnetic. All right, so our first one is the cobalt ion. So let's find cobalt in the periodic table. So there's cobalt right there. And we can see that cobalt is in the 4th row. We're going to have 4 orbitals. It has an atomic number 27, which means that we should have 27 electrons that we want to place, but we're dealing with an ion, right? And this ion has lost 2 electrons. So we're not going to worry about placing 27, but we are going to worry about placing 27 less 2, and that means we've got 25 electrons that we need to worry about, right? And I'm going to start by writing the electron configuration because that's what we're being asked to do. So I know that everything from the 3rd row and up is going to be full, so I can start with that. So for cobalt, I'm going to write cobalt first, and then we're going to alter it and write the cobalt ion. So for cobalt, we're going to have 1s2 and 2s2 and 2p6, 3s2, and then 3p6. All right, and then if we look at what we've got here, we've got 4s2, and then we've got 3d, 1, 2, 3, 4, 5, 6, 7. All right, so that's 7 for cobalt. And if we add all these numbers that we have here in the superscript, we're going to actually end up with 27. So 2 plus 2 is 4, 4 plus 6 is 10, 6 plus 2 is 12, plus another 6 is 18, 18 plus 2 is 20, and then plus 7 is 27. All right, so when we write our cobalt ion, we're going to have to lose 2 electrons. So where are we going to lose the 2 electrons? Are we going to take them out of the 3d orbital? We're going to take them out of the 4s. Well, we're going to actually eliminate the ones that are furthest out, which means we're going to eliminate the 4s electrons. So when we write the electron configuration for cobalt, the cobalt ion, it's going to be everything, including the 3p6, and then we're going to include the 3d7. All right. Now, if we want to write an orbital diagram, everything up to 3p6 is going to be argon. Argon is our noble gas right here. And so anything that we would list in the next beyond that, which would be the 3d elements, excuse me, the 3d electrons, we're going to make note of those. So this is how we would write that. So if we're going to do the orbital diagram for this, we're not going to put anything in 4s, but we're going to fill the 3d with our 7 electrons. So we do the kids on the bus rule, where we fill the squares singly first, and then we come back and then we add the last 2. And that's what our orbital diagram looks like. Now, based upon this, we can make the determination whether it is paramagnetic or diamagnetic, and this one is going to be paramagnetic. Now, the next one, they want us to do the nitrogen ion. All right, and we know here's nitrogen in the 2nd row, 2 orbitals, 7 electrons in the ground state, but this is gain 3 electrons. That's where that -3 comes into play. And so we're actually got 10 electrons that we're going to have to place. And we know that everything in the 1st row is going to be filled in. It's the 2nd row where we're going to have to manipulate a little bit. So if we write the electron configuration for nitrogen, we know we're going to have 1 s2, and then we're going to have 2 s2, and then we're going to have 2 p1, 2, 3. All right. So the question is, well, the question isn't whether we're going to gain or lose these electrons. We're actually going to gain through those 3 electrons. So when we write the electron configuration for the nitrogen ion, it's going to be completing that 2p subshell with 6 electrons. All right. So then if we fill in the orbital diagram, it's pretty simple for this one. So we can fill in the first orbital there, and then the first subshell of the second orbital, and then kids on the bus rule for the 2p, and then fill it in for the next 3. And I put these 3 in red so that you can see that these are added. These are the additional electrons that we added, thanks to this one becoming an ion. And based upon our orbital diagram, we can see that this is going to be diamagnetic. And for the calcium ion, if we find calcium in the periodic table, here it is in the 4th row, 2nd column. And we got 4 orbitals. At ground state, it would have 20 electrons that they want us to place, but we are a positively charged ion, which means that we've lost some ions, and in this case we've lost 2, so we're going to have 18, not ions, electrons. We're going to have 18 electrons that we need to place. So if we start by doing the electron configuration for calcium, we know that everything up to the 3rd row is going to be filled in. So we're going to have 1s2 and 2s2 and 2p6, and then 3s2 and then 3p6. All right. And then as for our 4th row, we're going to have 4s2. All right. Now, when we talk about the calcium ion, we've lost a couple of electrons. Which one are we going to lose? We're going to lose the outer 2. So then that's going to mean that the rest of the configuration for the calcium ion is going to look like this. Everything up to the 3p6. And then if we fill in the orbitals for this, the orbital diagram, we've got the first orbital filled in, 1s is filled in, and then the subshell for the second orbital is filled in, and then the p subshell. All right, kids on the bus, and then come back and fill it in, and then 3s gets filled in, and then 3p, kids on the bus, everybody gets filled in singly, followed by doubly. And if we look at this, then we can make a determination that the calcium ion is also diamagnetic. All right, in problem 3.8, they want us to choose the atom or ion that is the larger. So they're giving us potassium and its ion, fluorine and its ion, and then they're having us compare the chloride, which is the ion of chlorine, and then the calcium ion. All right, so let's start off with potassium. So potassium is here, and then the potassium ion would basically mean that we have lost that valence electron, right? And we can say it resembles argon. It doesn't exactly, but its electron configuration will resemble that, but we're going to have that additional proton. So based upon this, we can make the determination that the potassium atom is going to be larger than its ion because we've lost something in that outer orbital, which would make the ion the smaller. And there is a trend that a positive ion is going to be smaller than its atom. That tends to be the case. All right, let's take a look at fluorine. So fluorine is right here in the chart, and if we do the fluorine ion, it's going to closely resemble neon, except we don't have the same number of protons. So in this case, by adding that additional electron, we're going to get a slightly larger orbital in the ion than we would have in the atom. So the fluorine ion is actually going to be what's larger. And the trend with our negatively charged ions, or our anions, is that they have a tendency to be larger than the atom from which they were formed. All right. Now, if we were to take a look, we're going to take a look at chlorine and we're going to take a look at calcium. Now, chlorine is here. And if we add an additional ion, I'll get it out in a second, electron to chlorine, it's going to cause its electron configuration to resemble argon. But we're not going to have as many protons to hold that additional electron in. So we're going to have a slightly larger diameter species with the chlorine ion than we have with the chlorine atom. Now, what's going to happen with the calcium ion? Well, here's calcium, and we know that calcium is going to lose its 2 outer valence electrons, and it too will resemble argon. So then what's the difference? Well, calcium is going to have more protons, which means it's going to have greater nuclear effect, which means it's going to be able to hug those protons in a little bit more tightly and cause that its orbital to be a little bit smaller. So between the chlorine ion and the calcium ion, that means then that the calcium ion is going to be the larger of the two. So it really boils down to the nuclear effect. Chlorine has fewer protons to hang on to those electrons in the valence orbital than calcium does. Calcium is going to hang on to those valence electrons much more tightly and bring them in much more closely. So problem 3.9 wants us to determine which of the two elements has the highest first ionization energy. So probably need to define what the highest first ionization energy is, and that is the energy required to remove that first electron from the valence orbital. That's what that is. And if we just take what we know about the periodic table, we know that elements over here have a tendency to release electrons to form ions, where elements over here have a tendency to gain electrons to form ions. So just based on that information, we can figure out that maybe ionization energy is pretty low over here because they come up pretty easy, and then because these guys not only hang on to what they've got, but they can actually take on a few extra, probably have higher ionization energy here. And indeed, that is the trend. All right, so we get greater energy, ionization energy, as we go to the right. Now, what about as we move within a column, what do we see? Well, actually, the elements that are smaller have greater pull on the electrons that they have, and so what we're going to see is an increasing ionization energy, first ionization energy, as we go up a column. So, and the reason why is because the nuclear effect has a tendency to keep those electrons in their outer orbitals pulled in a little bit more tightly. But every time you add an orbital, those electrons get further away, and the nucleus is going to have less and less effect. So it requires less energy to pluck them off. Okay? So let's take a look at the first two pair of elements they want us to take a look at. So here we've got tin, and then we've got iodine. This one's pretty easy because we're in the same period, we're in the same row, and the one that is furthest to the right is going to be the stronger, and that's going to be iodine. Calcium and strontium. Here's calcium, here's strontium. Those are in the same column. And we know that the one that's further to the top is going to have the greater ionization energy, and that's going to be calcium. All right, our next pair is going to be carbon and phosphorus. Okay, so when they're close like this, we probably pretty much learned that these are going to be too close to call. All right, but I have a little something to say about this. All right, now the answer is it's too close to call, but I would say that it's more likely going to be carbon. Okay, and we could make this determination if we think about it. So what kind of ion does carbon form? Carbon doesn't form an ion. It doesn't form a positive ion. It doesn't form a negative ion. So carbon has a tendency to hang on to its electrons. Now, is the nucleus of carbon enough that it's going to pick up some additional? No. Some additional electrons? No, it's not. But it is strong enough that it's going to hang on to the electrons that it has. And the nature of carbon is that it forms covalent bonds with other elements. It doesn't have a tendency to enter into any sort of ionic bonding. All right. So that's the nature of carbon. Now phosphorus, on the other hand, sure, it has the ability to hang on to its electrons and gain a few extra, and it's a little bit further away from the left-hand side, close to the right. So we might think that phosphorus would be the stronger of the two, but carbon's higher up. So, you know, which one comes into play more? Well, I think at this point the author really didn't want you to have to suss this out and make a big determination, but what I would say is this. When you look at carbon and you look at the fact that it only has 2 orbitals and that it has the perfect number of electrons that will, not electrons, protons to hang on to its electrons, it likely has the higher ionization energy than phosphorus does. But the author wants you to be able to look at something like this and say that it's really too close to call. All right, that's really what this exercise is about. But if we were to kind of talk it out in class, that would be the argument that I would make, and I believe that is the case. All right, let's take a look at something that's not going to be so hard to make a determination about. Here's fluorine, and here is sulfur. And you're like, oh, but they're so close. Isn't that a lot like carbon and phosphorus? Well, let's take a look. Fluorine is further to the right, which makes it larger than sulfur, and it is also higher up, which makes it larger. So on two accounts, fluorine is going to be the larger. So our last question is another one based upon periodic table trends, and it has to do with metallic characteristics. So what are the trends regarding metallic characteristics? Well, the further to the left that elements are, the more metallic they are. And within a column, the further down we go the column, the more metallic we see, the more metallic characteristics that we see. So these are our two trends. And so we're going to have to make determinations between a couple of elements, just like we've done in all the other examples looking at trends. So our first two are going to be germanium and tin. So this one's pretty easy because we're in a column, and we know that the one that is lower in the column is going to be more metallic, so that's going to be tin. Our next two are gallium and also tin. And let's see, gallium is going to be more metallic because it goes to the left, further left than selenium. But selenium, not selenium, tin is further down. And this is really a scenario where it is too close to call. Yeah, this one's too close to call. Our next two are going to be phosphorus and bismuth. Again, we're looking within a column, and we know that the further down you are in a column, the more metallic you are. So that's going to make bismuth are more metallic. And then the last two, boron and nitrogen. And we know that the further left you are, the more metallic you are, and that's going to bring us to boron. All right. So with these trend questions, you really need to have an understanding of how the trends work. And honestly, I would probably take a little representative periodic table and then just draw the arrows on my trends to indicate my trends and make sure that you had that all of that labeled clearly, because they're just because it goes from left to right doesn't necessarily mean it's going from up to down. You know what I'm saying? So make sure you got those characteristics clearly outlined somewhere in your notes. And with that, we are done. Thanks for watching.